Okay, so welcome to week 1 of Unit 4 of Specialist Maths. And as you can see, week 1 is all about differential equations. So we're going on from our applications of calculus, which we did in the end of Unit 3, where we worked out things like area, volume and arc length. We're going on and we're using our differential equations to solve other kinds of problems. So differential equations are equations that have derivatives in them, basically. So let's have a look at a classic old-fashioned problem. Let's see. This is an old riddle from Lewis Carroll. Do you know who Lewis Carroll is? Anyone know who Lewis Carroll is? Heard of Lewis? Yeah, he's an author. He wrote Alice in Wonderland. And he was also a mathematician. In that, his pen name was Lewis Carroll, but his real name was George Dodgson, I think. Anyway, so he's got this little riddle here. So if we have 6 cats can kill 6 rats in 6 minutes, how many cats will be needed to kill 100 rats in 50 minutes? So this is a rates problem. So 6 cats can kill 6 rats. 2, you're saying, Sam. 2, you only need 2 cats to kill 100 rats. 6 cats can kill 6 rats in 6 minutes. How many rats can 1 cat kill in 6 minutes? We're assuming here that all cats are equally effective killers of rats. So all cats can kill rats at the same rate. So 1 rat per minute. 6 cats kill 6 rats in 6 minutes. So does that make actually 1? Yeah, Joel is right. 1 cat kills 1 rat in 6 minutes. So it requires a bit of clear thinking. So even when you have 6 rats and 6 cats, it still takes 6 minutes to kill all the rats, because this is the rate that cats can kill rats at. So have a think, how many cats do you need to kill 100 rats in 50 minutes? So if 1 cat can kill 1 rat in 6 minutes, 6 cats, if this is 6 cats, how long does it take 6 cats to kill 1 rat? Gosh, this is terrible. Hi boys, rats are dying. What do you think? 6 cats to kill 1 rat? 1 minute. 1 minute. 1 minute. Remember, that's 6 cats can kill 6 rats in 6 minutes. Now, if you only have 1 rat, the 6 cats can kill it in 1 minute. Okay, so here we go. So 6 cats can kill 6 rats in 6 minutes. So 1 cat kills 1 rat in 6 minutes. 1 cat can kill 100 rats in 600 minutes. It's 1 cat's rate of killing. So what we want to do is we want to work out how many cats we need to kill 100 rats in 50 minutes. So 600 minutes is 12 times 50. So we need 12 cats to do that job in 50 minutes. So the answer is 12. Have a think about that one. It's not going to be on the end of your exam, so don't worry. So we're going to just formally look at the mathematical conventions for setting up differential equations, and sometimes the abbreviation for that is DE. DE, differential equation. So a differential equation has at least one derivative term in it. So dy dx equals 2x plus 2 is a differential equation. And to solve that, what do we do? If we want to solve this in terms of y, what do? you integrate both sides. Yet you find the antiderivative. And when you do that, you end up with a constant of integration if there are no other conditions, because if you look at, you get a family of curves, a family of functions. So dy dx is the same for each one of these. Okay, because we don't know what the constant of integration is, so we put when we work out the antiderivative, we just put 2x plus whatever it is. Sorry, that's not right. If we do the antiderivative, just cross that out, we've got y equals x squared plus 2x plus c. So this forms a general, what's called a general solution. So we can find a particular solution if we are given some initial condition. So we can narrow down the c, we can work out what the actual equation is if we know either some known values or some other values. We've got some conditions, we can find a particular solution, which means just one solution. So if we know one value, we can narrow down to a particular solution and evaluate the constant of integration just by substitution. So we find the general solution by integration. We get that family of curves, a family of curves because we have the constant of integration. And if we have an initial condition, we can satisfy and find out a particular solution. So this is just terminology. Okay, so you've got the general solution and you've got a particular solution. A particular solution satisfies some condition of an equation. So let's look at some examples. So here's another example of a differential equation, except this one has got two derivatives in it. It's got dy dx plus 2y times dy dx equals x plus 5. So we can rearrange this equation. We can factorize that left-hand side, take out, we've got dy, we can take out dy dx as a common factor. 1 plus 2y equals x plus 5. And then we can divide both sides by 1 plus 2y, and we end up with isolating dy dx. Okay, so what about this equation? How do we solve this equation? That is a little bit trickier. How do we solve this equation? A little bit trickier. We can integrate both sides. We're going to look at some methods of, we can do the separation of variables. We can get a general solution like that, because this derivative is dependent on the x and the y. So for different values of x and y, the gradient changes. It's not the same for the. Usually, if it's just dy dx as a function of x, the gradient is the same for all values of x, but this one changes with y as well, dependent on x and y. So this might show the general solutions for a differential equation, and you get a family of functions again, but if you have some initial condition, you can evaluate and find a particular solution. So a particular solution, you might be able to evaluate that, and it might be a particular solution over there, like so. Okay, so alright, so we've got different classifications of differential equations. They have first order differential equations. They just have a first order derivative in them. So they have dy dx equals f of x, and then you just take the antiderivative to find y. And maybe if you've got some known initial conditions, you can evaluate a particular solution. So otherwise, if you don't have some known conditions, you get a general solution. So this is just dy dx equals this expression, this quartic. You take the antiderivative and you evaluate a general solution. Pretty straightforward. So that's a general solution for a differential equation. Second order differential equations have second order derivatives in them. So they have second derivatives in them, and they can be a combination of second derivatives, first derivatives, and just the terms without derivatives. So you might have to do anti-differentiation twice to find the general solution for second order differential equations. So here's an example. So you have the second derivative is equal to cosine of x. So to find the solution for this case, you take the antiderivative to find the first derivative. So the antiderivative of cosine of x with respect to x is sine of x plus the constant of integration. And then you have dy dx equals sine of x plus the constant of integration. Then you have to integrate again. You integrate that expression with respect to x to find the equation in the general form, and now you have two constants introduced there. Okay, so you might have to take the antiderivative twice if you have a second order differential equation. So this is sort of stuff you know, but just sort of putting it in context that they're used in application problems a lot, differential equations, because they're describing rates usually. So if we want to set up differential equations, they usually come from worded problems. So this is a classic example called Newton's law of cooling. I don't know why. I guess maybe he was the first one to observe it. So this is an observation that the rate at which a body cools is proportional to the difference between its temperature and the temperature of its surroundings. Okay, that makes sense. So if you make a hot cup of tea, after a period of time, the tea, if you don't drink it, goes to room temperature. So this is basically trying to model the cooling rate of a hot object. So what it's saying is the rate that it cools is proportional to the difference in the object's temperature and the temperature of its surroundings. So the rate of the temperature change, the change in temperature over the change in time, that's what that is proportional to the difference between the temperature of the object and the temperature of its surroundings. And this little thing that looks like a fish means proportional to. Okay, I don't know if you've ever seen that before. So what does that mean? This means that this, if it was just a hot beverage or a bowl of soup, is cooling. And why is it negative? Because the soup is hotter than the surrounding room temperature. So the temperature is decreasing of the soup, is decreasing over time, so it has a negative rate of change, and it is related to the difference in the temperature of the object and the temperature of the room. So this is turning a proportional worded problem into a actual differential equation of first order, because there's one derivative there and there is some constants there. Minus k is a constant, and the temperature of the room, temperature of the surroundings, is also a constant. So this is setting up a differential equation, and how might we solve it? Okay, so this is your bowl of soup. It starts off at almost boiling point, 90 degrees Celsius, and over time, if you don't touch it, it goes to the temperature of the room, which may be 20 degrees Celsius. Okay, so this is what happens to a bowl of soup left untouched in a cold room. So here's our equation, our differential equation. So we want to solve that. So if we want to solve that, we need to observe some things about the differential equation. It's dt, the change in temperature of the change in time is proportional to the temperature. So if we want to take the antiderivative of this, it's easier to use the reciprocal, because on the right hand side it's a function of temperature, not a function of time. So can you see here we're just taking the reciprocal and expressing the change in time with respect to the change in temperature. Can you see that? And now we can work out time integrating both sides with respect to temperature gives us an equation for time. And I've taken negative 1 over k out as a constant, and we're left with this expression here. Which is something you should be able to integrate. Now remember, t subscript s is a constant number. That's the temperature of the surrounding room, which is a constant. So which integral, looking at this, what integration rule can you apply to integrate this particular integrand? Natural log, yes, because it's actually, the integrand is 1 over t, in fact, with some constant in it. So the natural log, so looking at that, if we look, this is the natural log. We've integrated now this expression. It's the natural log, the difference in the temperature and the modulus sign there, plus a constant of integration. So this is on our way to solving the differential equation. So we can rearrange this, and we can do some things with exponentials and logs to make this equation a lot simpler to solve. So first of all, we can take away the constant of integration from both sides. Okay, then we can multiply both sides by negative k. And then we can put both sides as powers of e. Raise both sides to as powers of e, and then we can resolve the right hand side. So e to the power of negative k, open bracket t minus c, equals the difference in temperatures. Can you see that algebra there? Are you able to follow these algebraic steps? So now we've got this expression. Now this expression, if you remember your exponent rules, you can expand that out. That is the same as e to the power of negative k t plus kc. Can you see that? Now, if we let e to the power of kc equal another constant, we can define that, then it becomes a lot simpler to solve, because e to the power of negative kt times e to the power of kc, we can rewrite that. If we let a equal e to the power of kc, we can rewrite that as so. You see that? And that's a lot easier to solve. If we know some initial conditions about the temperature of things, so at t equals 0, the temperature of the soup is T0. So we can substitute that in, and we can work out what A is. Because A is going to be the difference of the soup initially with the surrounding room. That's the A. And then we can actually set up the equation. So it's almost solved. T minus S is equal to A, and we worked out A is the difference of the temperatures from the initial temperature of the soup till it gets to the surrounding temperature of the room, and this becomes that equation. And just rearranging that, adding the temperature of the room to both sides, gives us the final form of the equation, and we've solved the equation. How about that? So that's the solution. Okay, here's another example. This one is radioactive decay. So the rate at which a radioactive substance decays is proportional to the mass of the substance remaining. So this one is dm dt, where m is the mass of the substance. Now what do you think the rate will be, negative or positive for the radioactive decay? Which way are we predicting the rate of change of the mass is going to be? Negative. Yes, the mass is becoming less. But it says to us here that the mass, the rate of decay is proportional to the amount of mass remaining. So we use that to set up the equation. The rate of change of the mass with respect to time is proportional to the mass that remains. And we can set up a differential equation. So the rate of change of the mass with respect to time is equal to negative Km, where K is some constant. And it's negative because it's decreasing, as we said. So this one's fairly simple. So this is what's happening. Radioactive decay over time. And this is the differential equation that we have. The rate of change with respect to time is a function of m. So what do you think we have to do to resolve this differential equation? It's pretty similar to the one we did previously. What do you think we need to do? Flip it, yes, we take the reciprocal. We take the reciprocal, we've got this, but we can't resolve that because it's a function of m, so we need to take the reciprocal. dt over dm is the reciprocal, negative 1 over km, where the mass remains positive, greater than 0. So if we do that, then we set up a differential, set up an integration, and it's pretty easy to integrate. We can take out that negative 1 on k at the front there as a constant, and now it's a very simple integral. We're going to get a natural log. So t is equal to negative 1 over k, natural log of m plus the constant of integration. Now hopefully then we have enough information. We've got a general solution. We could work on a general solution and simplify that. And hopefully we have enough information to work out a particular solution as well. So using a similar technique to before, subtract the constant of integration from both sides. Okay. Multiply both sides by negative k. Now we've isolated on the right hand side, we've got natural log of m. Now if we raise both sides and make them powers of e, then we can isolate m to be equal to e to the power of negative k, open bracket t minus c, which we can expand. And if we let a equal the constant part, e to the power of kc, remember that's just another constant, we can simplify this even further, and we've got an equation, mass is equal to a times e to the power of negative kt. Now we have to define that a, it just can't appear magically. We've got to define what that a means. And this is a common way of expressing the solution in its general form. So hopefully we have some initial conditions or some conditions where we can find a particular solution. So maybe we have the initial mass, maybe that's given to us at time t equals 0, the initial mass of the object that's decaying. And if that's true, if the at t equals 0, if we know that m is equal to 0, what happens if we have here m0 is equal to a e to the power of negative k times 0, which is basically going to let us resolve what a is. A is the initial mass, which allows us to set up the equation. So this equation, the solution for it, the particular solution, if we know the initial mass is m, equals the initial mass times e to the power of negative kt. We still haven't resolved it. We haven't worked out what k is. We need another condition to help us work out what k is. We have two unknowns, so we need two known points on the function or the graph to help us work out the particular solution in this case. Okay, here's another one. So this one, we've got a population. The population growth, the rate of change, dp dt, is proportional to the square root of the population, the current population. Okay, so this is setting up the proportional statement. The rate of change of population with respect to time is proportional to the square root of the population. So the population is growing, I guess, so this is a positive k here. We could work it out anyway if we had some initial conditions. The rate of change of population with respect to time is equal to k times the square root of p. And again, this is dp dt as a function of p. Again, you need to take the reciprocal. Can you see? And then we take the next steps. So we take the integral here. Oh, we just use that polynomial rule to take the integrand, to integrate that expression, and we've got a general solution. T equals 1 over k times 2 times p to the power of 0.5 plus c, and by some fancy algebra we rearrange that, and then we can express the population as a function of time. We have two unknowns here. We have got k and we've got c, which came from the constant of integration. So we would need 2 points. Maybe we need the initial population at t equals 0 and then some other measure of the population, maybe after 2 or 3 years, to be able to establish what the k and the c are to give a particular solution for this example. Okay, so we're going to look at some techniques for integrating where we may not be able to take the reciprocal to integrate. So say we have a differential equation of first order that looks like this, which we've already seen before. So we take out dy dx as a common factor. We do that, and then we can separate the variables. See what I've done here? So this is dy dx times open bracket 1 plus 2y equals x plus 5. If we multiply both sides by dx, we have in fact separated the variables. So now we can integrate both sides independently. Now this technique is called separation of variables, and now we can take the integral on the left hand side with respect to y and on the right hand side with respect to x, because all the variables on the left hand side are as function of y, and all the variables in the integrand on the right hand side are functions of x. So that's called the separation of variables technique. So we just keep on going. So we've integrated on the left hand side, we've got y plus y squared. Now that could have had a constant c0, and integrating on the right hand side we've got a half x squared plus 5x plus c1. But because we can just combine the constants, just combine them, doesn't matter. That could be c1 minus c0. Doesn't matter what the constant is, it's still going to be a constant. We can just simplify it. Okay, it can just be simplified. So here's another example of separation of variables. So we've got a population growing at a rate of 1.3 times the current population per minute. At the beginning, at t equals 0, there are 80 people present. How many people present after 100 minutes? Okay, so hopefully we can work this one out. We're told the rate of change of the population, we're actually given that k, that constant. It's growing at a rate of 1.3 times the current population. So we have an expression here that's a differential equation expression. Now what could we do? We could flip it again, but it's actually easier to, in this case, integrate it, find the antiderivative by doing separation of variables. It's just a technique like all those other integration techniques. Sometimes it's handy to know when to use which one. We have an initial condition here. At t equals 0, the population's 80. So we want to find what is the population at t equals 100 minutes. So we're given that value k, proportion factor, so we've got to integrate. So we've got dn dt equals 1.3n, so we can separate. We're assuming lots of things, that n is continuous, which is hard for people, but anyway, we'll assume that. So see here, separated the variables. What have I done? 1 over n dn is equal to the integral of 1.3 with respect to t. The integral of 1 over n with respect to n is equal to the integral of 1.3 with respect to t. I multiplied both sides by dt, and I divided both sides by n. Can you see that? You would have to add t is greater than 0, yes, but generally when it's a population thing, spec forward -1, it might say that already in the initial problem. So here we've separated the variables. So what's the antiderivative of the left-hand side? The antiderivative of 1 over n being integrated with respect to n is natural log of n. The antiderivative on the right-hand side is going to be what? Antiderivative of 1.3. That's a pretty simple one. Yeah. And we have that constant of integration. So doing this, we are going to integrate. I think it goes on to the next page, or does it not? Okay, it goes on to the next page. So this is our general solution. Oops, there's our general solution right there. Right, so that's integrating the left-hand side, the right-hand side, and adding the constant of integration in there. Okay, and this technique we did was by separation of variables, and it was a lot easier than using the reciprocal. We didn't have to worry about exponentials and all sorts of things. Sometimes we can do it this way. We need to just practice lots of problems so we can recognize that straight away, which technique we can use. So now we can keep on going. So this was just rearranging that. Hang on, I rearranged that. So this is now n. If we raise both sides, it's going to be e to the power of 1.3 t plus c. Are we in agreement there? So that's raising both sides, making them exponents, making both sides exponents of e, and we can rewrite that as n equals a e to the power of 1.3t. If we let a equal e to the power of c. How's that? This looks okay. We're on our way to solving this general solution. So that's what's on the next page here. So kind of there, and then we've introduced let a equal e to the power of c, and so we've got this expression here. So we know at t equals 0, when t is equal to 0, the population was 80, so then we can evaluate what a is. A is equal to 80, and then we have solved the equation. We have an equation representing a particular solution for this particular population. N as a function of time is equal to 80, then e to the power of 1.3t, and then they wanted us to answer the question, at t equals 100, what's the population? Simple substitution. Substitute into the equation, and we have the answer. That's a lot of people. Got 10 to the power of 58. That's quite a lot. They're growing pretty fast, that population. Holy smokes, I know. Okay, so another example of using differential equations that is quite challenging when you first look at these kind of problems are mixing problems. So mixing problems have differential equations describing the rate of change where something is going into an object or entering a room, but leaving the room at a different rate. Entering the room at one particular rate, leaving the room at another rate. Entering a water tank at a particular rate, leaving the water tank at a different rate. So there's a couple of different scenarios when the input flow rate is equal to the output flow rate. This is the easiest scenario. And what do I mean by that? So let's have a look at an example. So a tank, say, contains 1 kilogram of salt already dissolved in 100 litres of water. Salty water is added to the tank at this rate. 0.25 kilograms per litre of salt is in the water added, but it goes in at a rate of 4 litres per minute. Stirred thoroughly, solution is drained from the tank at 4 litres per minute. How much water or how much liquid is in this tank at any time? If the input rate is equal to 4 litres per minute going in and the output rate of liquid coming out is 4 litres per minute, how many litres it remains constant? Yes. So this is when the input flow rate equals the output flow rate. The amount of liquid total remains constant in the tank. What is changing, if you look at the question, is the amount of salt in the tank. Because the amount of salt in the tank, well, it's got 1 kilogram of salt to start with, and then salty water is going in at a rate of 0.25. And how much is coming out? I don't know. Let's work it out. So this is asking us, how much salt is there in the tank at any time? So we don't know. So we're going to define a variable. S is going to be the amount of salt in the tank as a function of time. So we just define that. We let S be, S is a function of T. We know at T equals 0, there is 1 kilogram of salt in that tank. Okay, that's all we know. So we already talked about how much liquid is in the tank. The inflow rate of liquid is 4 litres per minute. The outflow rate of liquid is 4 litres per minute. So this is how much salt, though, is going into the tank. The amount of salt going into the tank is 0.25 kilograms per litre, and there's 4 litres going in. So there's 1 kilogram per minute of salt going into the tank. The tank has 100 litres of water in it, so we don't know what the current concentration is of salt at any time, but it is the amount of salt divided by 100 litres. Okay? And that's the current concentration at any time, and it's being siphoned off at a rate of 4 litres per minute. So S over 100 times 4 gives us the rate of salt leaving the tank, which is S over 25, simplifies to be S on 25 kilograms per minute. So we can set up a differential equation. The rate of change of salt with respect to time in this tank is the amount going in minus the amount going out. The amount going in, you might like to set up a table. Sometimes students like, when you're first looking at these problems, how do you set it out? How do you look at it? A table is useful. You don't have to use a table. You might be able to work it out without a table. But a table is useful because something's going in and something's going out. Something's going in at a rate of 1 kilogram per minute for the salt, and the salt is being mixed. We don't know the concentration at any time, but it's coming out. S over 100 is the concentration, coming out at 4 litres per minute, which simplifies to this expression. So this is the differential equation describing the amount of salt in this particular tank at any minute. 1 minus flow in minus the flow out. Okay, so we've got a differential equation now. So we can set up and solve that one. And what method do you think we might use to solve this one? It's ds dt, simplifying that, is 25 minus S over 25. We could do a couple of different things. What have we learnt about or looked at in this lesson so far? What methods could we use? We could take the reciprocal and integrate, yes? Could we separate the variables? We multiply both sides by dt, we'll get ds equals 25 minus s on 25 dt. Yeah, we could separate the variables, couldn't we? We could then multiply by 25 on 25 minus s ds equals 1 dt. Is that doable? And then we can integrate both sides. We could do that too. Either way, it's going to be yucky. even though it's going to be yuck. But maybe separation of variables is an alternative technique to consider. Oops. So here we go. So I didn't do that this time. I just did the reciprocal. Okay, and then integrating dt ds with respect to s this time, and just evaluating, do all that algebra, don't make a mistake, do all that algebra, integrate, find the constant of integration, because at t equals 0, the amount of salt in the tank was 1 kilogram, evaluate the constant of integration, put it back into the equation, use your log laws to try and simplify all of this, don't make a mistake, simplify, and do we get the final answer? Where's the final answer? Here's the final answer after simplifying and applying all our algebra. Okay, does it make sense? The salt in the tank should be increasing. So is it increasing? At t equals 100. How much salt is in the tank? Yes, it's getting more. The salt in the tank is increasing. Okay. Let's have a look at some other kinds of problems. Okay. This one, let's have a look at this one. So this time the tank has got 1 kilogram of salt in it, in 100 litres of water. It's looking the same as the one before. Salty water is poured in at a concentration of 0.25 kilograms per litre at a rate of 4 litres per minute. This time it's drained at a rate of 2 litres per minute. How much salt in the tank at time t? How much liquid is in the tank? What's happening to the amount of liquid in this tank in this scenario? 4 litres per minute is going in, 2 litres per minute is coming out. The litres per minute, the volume is actually increasing. How much is it increasing by? 100 to begin with, plus, could you work out an equation? It's increasing by 2 litres every minute, right? So this would be the volume of liquid in the tank at any time. So this is also thinking. It's just not just apply a formula, just blindly go there. This is the volume in the tank at any time. Where t equals 0, the volume in the tank is 100 litres. At t equals 1 minute, the volume in the tank is 102 litres. At t equals 3 minutes, the volume in the tank is 106 litres. So it's increasing by 2 litres every minute. So we need to keep that in mind when we're setting up the differential equation in this case, because this time the input flow rate exceeds the output flow rate, so the volume in the tank is increasing. So that's important. So if we set up a little table to help us work it out, the inflow rate of liquid is 4 litres per minute, the outflow of liquid is 2 litres per minute, which means the volume in the tank is increasing. But what about the salt? What about the salt? The salt is going in at 0.25 times 4 kilograms per minute. Concentration times the litres in. So the salt is going in at 1 kilograms per minute, and the concentration of salt is S, which we don't know, an unknown, but the liquid is increasing. So now the concentration is S divided by 100 plus 2t, because the amount of liquid is increasing over time. And this is the concentration at any time, and there is 2 litres leaving the tank. That's the rate of litres coming out of the tank. So we multiply those two together to get the out rate of salt. And simplify that as much as possible, and we have a differential equation. 1, the rate of change of salt with respect to time is equal to 1, which is the in rate, minus the out rate, which is S over 50 plus t. Now, that's all we can do here so far in our course. When you go to university, you might be able to solve this one. But for now, We don't learn any techniques in Specialist Maths Year 12 to be able to solve one like this because we can't actually separate the variables. We can't use the reciprocal to separate the variables. Basically, this is it. Now, you could be asked a question like this at the end of the year where you're just asked to set up the equation, but not solve it necessarily. Okay, so we've done the input flow rate equals the output flow rate, and we've looked at the input flow rate exceeding the output flow rate. One more, where the input flow rate is less than the output flow rate. So here we go, same salt, salty water. 1 kilogram of salt is in 100 litres of water. Salty water is going in at this concentration, 4 litres per minute, stirred thoroughly, drained from the tank at 5 litres per minute. Now what's happening to the volume of liquid in this tank now? It's decreasing. Can we write an equation for the volume decreasing? 100 minus T, Yep, that's exactly right. Thank you, Charlie. So, at 1 minute after this experiment, we're going to have 99 litres of liquid in this tank. 10 minutes after the experiment starts, we're going to have 90 litres. So it's getting less and less liquid in it. So setting up a table to help us work out the differential equation. So we've got the liquid going in at 4 litres per minute, going out at 5 litres per minute. This gives us the volume equation with respect to time, because we need to know that to work out the concentration of salt. The salt is going in at 1 kilogram per minute. The salt is going out at the concentration of salt is S over 100 minus T at any time. 100 minus T is the volume of liquid, leaving the tank at 5 litres per minute. So we multiply those two rates together. We have the salt is leaving the tank at 5S over 100 minus T. Setting up this differential equation, the rate of change of salt is the difference between the input rate and the output rate. And again, cannot solve this one with the techniques that we have learnt in Specialist Maths Year 12. So all we can do is set up the differential equation. The only ones we can solve are the ones where the input rate equals the output rate. So, anyone have any questions? I'm just going to stop this recording. T is restricted between, yes. Why is that? Special 1 has made an excellent point. In this case, T will only go for 100 minutes. Yes. And then the tank will be empty. And that's it. Okay, let me just stop this recording.